In the world of physics, we've got these two absolute titans, Einstein's general relativity and quantum mechanics. For more than 100 years, they've been the undisputed champs, each one ruling its own kingdom and honestly acing every single test we've ever thrown at them. But here's the cosmic catch. These two perfect, beautiful theories are built on ideas that just don't work together. They're fundamentally incompatible. So, what happens when the two gods of physics have a major disagreement? Well, that is the biggest, most profound question in all of physics today. Okay, so let's really dive into this. To get a feel for the clash, we first have to get to know our two main players, right? These are the foundational theories that literally describe our entire universe. So, in one corner, you've got general relativity. This is Einstein's masterpiece. It flawlessly describes the universe on the grandest scale you can imagine. We're talking planets, stars, galaxies, the whole cosmic dance. And in the other corner, you've got quantum mechanics, the undisputed champion of the tiny, microscopic world. It gives us the weird, wonderful, and unbelievably accurate rules for particles, atoms, and forces. On their own, they are perfect. But the moment you try to use them together, the whole thing just breaks. They completely contradict each other about the most fundamental thing you can think of, the very nature of space-time itself. And this, right here, gets us to the absolute heart of the conflict. And it really all comes down to a simple but powerful analogy. Is space-time just a passive stage where the universe's drama plays out? Or is it one of the main actors? See, in Einstein's picture of the universe, space-time isn't just some boring, static background. Not at all. It's an active, dynamic participant. It can bend, it can stretch, it can even ripple with gravitational waves. It's a key actor that influences absolutely everything that happens in the cosmos. There's this famous quote that just sums it up perfectly. Matter tells space-time how to curve, and space-time tells matter how to move. It's this incredible cosmic dance, right? Massive things like stars warp space-time, and that warping, that curvature, is what we feel as gravity. It dictates how everything else moves. The two are completely locked together. But then you have quantum mechanics, and it has a totally different take. For any of its math to work, it has to assume that space-time is just a fixed, rigid, unchanging arena. It's the stage where all the wild quantum drama unfolds, but the stage itself, it doesn't move, it doesn't do anything, it just sits there. And that's the core conflict right there. Is space-time a dynamic, flexible actor, like general relativity says it is, or is it a passive, rigid stage, like quantum mechanics needs it to be? They just can't both be right. Now, we can put some of the more official scientific names on these ideas. Give a little more structure to this actor versus stage thing. Because space-time is an actor, general relativity is what physicists call a background-independent theory. Think about it. It doesn't need a pre-existing stage to work, because the theory itself creates the stage as part of the whole show. It's independent of any background. Quantum mechanics, on the other hand, is background-dependent. It depends on that fixed stage being there first. It can only describe how the actors, the particles, interact on that stage. It has absolutely nothing to say about the stage itself. So, actor, stage, who cares, right? Why does this philosophical-sounding disagreement actually matter? Well, it matters in the most extreme, the most violent, the most mysterious places in our entire universe. There are a few very special, really mind-bending places where the world of the super big and the world of the super small are forced to collide. Think about the heart of a black hole, or the very first instant of the Big Bang. You've got immense gravity, that's relativity's turf, all crammed into a space so small it's squarely in quantum's territory. And right there, at those points, our physics just stops. It gives up. We need both theories to tell us what's going on, but because they're totally incompatible, their equations just spit out nonsense, answers like infinity. We literally have no language right now to describe these ultimate cosmic secrets. But hey, let's bring this all back down to Earth for a second. This isn't just some abstract theoretical problem. Einstein's relativity has a very real, very practical impact on technology you probably use every single day. Let's talk about the GPS on your phone. The satellites are way up there, moving super fast, and they're in a weaker gravitational field than we are down here.
Okay, so according to special relativity, their speed makes their clocks tick just a little bit slower, by 7 microseconds a day. But according to general relativity, the weaker gravity makes their clocks tick 45 microseconds faster. You do the math, and the net result is that their clocks run ahead of ours by 38 microseconds every single day. If we didn't constantly correct for that tiny difference, your GPS would be off by 12 kilometers every day. It would be totally useless.
And all of this brings us to the biggest, most exciting quest in modern physics. How do we resolve this epic clash of ideas? How do we find one single theory that works everywhere, from the GPS in your pocket to the very heart of a black hole? This mission, this hunt, is the search for a theory of everything, or what physicists more formally call a theory of quantum gravity. It is the absolute holy grail, one single, beautiful, elegant framework that can describe the entire universe with just one set of rules. Now, we're not there yet, but there are some really fascinating ideas out there. You might have heard of some of them. Theories like string theory, which says particles are really tiny vibrating strings, or loop quantum gravity, which suggests spacetime itself is made of tiny indivisible chunks. These are the kinds of ideas trying to crack this massive puzzle. At the end of the day, the ultimate goal is just to write the complete story of our universe. A single, consistent story that doesn't break down at the extremes, that can finally tell us what happened at the Big Bang and what's inside a black hole. A theory that finally unites the two great pillars of physics. Which leaves us with the biggest question of all. What is space-time really? Is it the passive stage for reality? Is it an active player in the cosmic drama? Or is the truth something even weirder, something our current science can't even begin to imagine?